Hi, Franklin Pierce family. I'm Dr. Ma. I'm the Assistant Professor of Exercise Physiology. In the past 3 years, Dr. Anzelin and I are working together in leading the lab of exercise physiology. Our lab focuses on exercise testing and prescription among athletes. We also look at the various health benefits of exercise. Last year, there were 6 students working with us in investigating the lactate threshold application among rowing teams.
Hello everyone, we are the student researchers here at Franklin Pierce's INBRE-NH INSPIRE lab. This year we focused on blood lactate levels in collegiate rowers and if blood lactate could be a valid indicator of 2K time.
Before we begin, I would like to highlight key terms within the presentation that revolve around our field of study. Let's begin with blood lactate. Lactate production is the result of glucose utilization of muscle cells under aerobic utilization, and it is an important gluconeogenic precursor, lactate distribution along the blood lactate recovery curve, which allows estimation of the net amount of lactate released during recovery from the active muscles. The production of blood lactate is a result of glycolysis. Next, we have lactate threshold. Lactate threshold is defined as the intensity of exercise at which lactate begins to accumulate in the blood at a faster rate than it can be removed. Moving on, we have dragging factor. The drag factor is the amount of resistance selected by a competitor on their assigned indoor rowing machine. Along with this, we have RPE. The Borg rating of perceived exertion is a subjective way of measuring physical activity intensity level. Perceived exertion is how hard you feel like your body is working. And lastly, we have maximal lactate steady state. MLS is defined as the highest blood lactate concentration and workload that can be maintained over time without continual blood lactate accumulation. In this study, we use foundational lactate threshold concepts to further validate our study and their credibility. A person's lactate threshold is the point at which lactate builds up in a bloodstream at a level that is higher than resting values. During the last nearly 50 years, the blood lactate curve and lactate thresholds have become important in the diagnosis of endurance performance. An intense and ongoing debate emerged, which was mainly based on terminology and the physiological background of lactate threshold concepts. Additionally, lactate threshold concepts shall be integrated within the aerobic-anaerobic transition, a framework which has often been used for performance diagnosis and intensity prescriptions in endurance sports. Usually, graded incremental exercise tests, eliciting an exponential rise in blood lactate concentrations, are used to arrive at lactate curves. A shift of such lactate curves indicates changes in endurance capacity. Along similar terms, the concept of the 4 millimoles per liter threshold value is referred and applied in this study and is used as a criterion for establishing aerobic and anaerobic thresholds.
Blood lactate is considered a valid performance indicator and is closely related to an athlete's maximal lactate steady state. Athletes can use lactate threshold to train by improving their body's use of lactate. The best way to do this is to consistently train at your lactate threshold, which is intense enough to increase your lactate level just before the point where it begins to spike. The spike is the point where your muscles begin to fatigue. This is a specific point and is different for each athlete, which is where our study comes in. By looking at a rower's lactate threshold, coaches can base training intensities, pre- and post-season fitness levels, and other factors on the difference in the lactate levels. They can also use blood lactate training to better their athletes and improve endurance. The most important application of blood lactate in regards to our study is the correlation between 2K time and lactate threshold levels.
For our study, participants were from both the men's and women's rowing team from Tufts University in Boston, Massachusetts. We had a total of 48 rowers in the study. Our research team traveled to Tufts on November 7th, 2021 for our first round of testing, and February 13th, 2022, we went back for our second and final round. We did 2 different testing dates to see the progress the rowers had made through their training program. We had certain pre-test conditions for the participants. They were asked to not consume caffeine, alcohol, or exercise before the test. Participants also had to be over the age of 18. We worked with the rowing coach at Tufts, Tom Siddall, and the participants were recruited through Tom as well. All participation was voluntary and there was no compensation for the participants other than having the data for their own personal use. This study was also approved by the Institutional Review Board. Before testing, the participants were required to fill out a standardized health status form and a physical activity readiness questionnaire. During the test, participants' watts and workload was determined by their previous 2K time. There were 7 rounds of 4 minutes of rowing and 1 minute rest. However, not all rowers completed all 7 rounds. The blood sample was collected at the end of each 4-minute rowing stage, so during that 1-minute break. We collected blood samples by pricking the participant's fingertip and obtaining 1 drop, approximately 0.7 microliters of blood, and used a lactate meter to analyze their blood lactate levels. Athletes were also asked how physically exerted they felt on a scale of 1 to 10, 1 being not tired at all and 10 being extremely exhausted. The lactate samples were collected until the termination of the test.
The data in this table is a necessary determination for test protocol. It is validated by the Australian rowing team. It's used for their national rowing team. We determine the watts for each participant through data from this table based on the athlete's best 2K time. The Franklin Pierce University women's rowing team performed 2K tests. A 2K test is a typical rowing test on an ergometer that covers a total distance of 2,000 meters. The goal of this test is to complete the 2,000 meters in as little time as possible. Stationary ergometers were used to perform this test. The lactate measurement was taken using a Lactate Plus meter, which was manufactured by Nova Biomedical in Waltham, Mass. This meter is used to determine the lactate levels of the rowers during their VO2 max tests. It is also used to determine lactate threshold. The blood is taken from the participant's fingertip and is measured in the Lactate Plus meter, and all meters are calibrated before analysis. All materials with blood were properly disposed of in biohazard waste baskets. Researchers wore gloves throughout the entire test, and testing areas and machines were disinfected between each participant.
This testing is meant to simulate a 2K race on the water, which is the most common length of race in the sport of rowing. The object is to finish in the fastest time possible. Each time is recorded for how long it takes to complete this distance. Due to our study being completed by college athletes, the average age was 19 years old. The average height for this study, 180 centimeters, is taller than the average height of the general population. Taller rowers are more efficient at rowing because they are able to get more length, therefore making better rowers. The average weight for this study, 78.9 kilograms, is higher than the average weight of the general population. Heavier rowers typically have more muscle and are able to pull harder than other individuals. The average years of experience was 5 years because rowers have been recruited to row from high school programs. Drag factor on the rowing ergometer is used to simulate the resistance of being on the water. The average dragging factor was 119. For lightweight women, the dragging factor is set to 100, 110 for heavyweight women, 125 for lightweight men, and 130 for heavyweight men. This table represents the average lactate level at each stage during the test. The trend shows an increase in average lactate levels at each stage, which correlates with the exponential curve of lactate threshold. Looking at the table, lactate level increases in a non-linear trend with each step. During the 1-minute break between each stage, each blood sample was taken as efficiently as possible in order to maintain the efficacy of the data.
To understand the next slide, it's important to explain the Pearson correlation coefficient. This type of graph describes the correlation of 2 variables. The range of correlation is from 0 to 1, with 0 representing no correlation and 1 showing perfect correlation. This slide shows an example Pearson correlation coefficient graph comparing years of education with income. We found that the strongest indicator of 2Ks were Gmax and modified Dmax. This was supported by the high correlation coefficient. Dmax shows the point on the regression curve that represents the maximal distance to the straight line formed by the 2 endpoints of the curve. In modified DMAX, the initial lactate data point is not used. Instead, lactate level after the first initial increase is used. This point and the last point are used to draw the line. As discussed previously, the closer the value to 1, the stronger the correlation. It is also important to use absolute value when looking at these numbers. The negatives that you may see in the chart above are irrelevant to correlation. The two highlighted values had the greatest correlation at 0.820 and 0.842, suggesting that Dmax and modified Dmax may be the best predictors of 2K time. In conclusion, the data showed that the best method for determining training zones and rowing performance among collegiate rowers may be Dmax and modified Dmax.
Future studies are warranted to investigate application of lactate threshold across different levels of athletes, including recreational and professional, to test the generalized ability of our results.